I think people are gonna still join in the next 1 minute, but we have quite a busy schedule ahead of us today. So we have 5 presentations from 5 academics. Each of the presentations is going to take about 10 minutes. First, before we start with the presentations, I want to tell you why we're doing these meetings. So we decided some years ago to gather together researchers and academics and people from NRENs to exchange ideas, research, and things that they're working on. Over time, we have experimented with different formats. We had the meeting open to everybody. We've had the meeting by invite only. And so there are different advantages and disadvantages to both. In the end, so for now, we decided to keep it to academics only in order to stimulate debate so that people can feel free to ask questions. Yeah, so welcome to the meeting. And then I also want to give our board member, Maria Hall, the opportunity to say a few words. Maria?
Yes, sorry, my phone was just ringing. I turned it off. Yeah, hello everybody. My name is Maria Hall, as Gergana said, and I'm a member of the RPNCC Executive Board since some years back, and I'm a CEO for the Swedish NREN, the Academia Network Sunet in Sweden. So actually, it was actually a dialogue between me and the RIPE-NCC when I became on the board that I would like to gather the NREN community and the academic community to actually to stimulate the debate, stimulate the engagement in the RIPE community, and actually bring up issues that could be of interest for us, of course, but also for the rest of the community. So as Gergana said, we had the different settings. We have been open meetings, we have been closed meetings, but of course there are advantages and disadvantages, both of them. But now everything is so weird when we just see each other on Zoom all the time. So I think it's a good setting to have it this way this time. So I'm saying thank you very much, Gergana, once again for arranging this. And well, I hope that we someday in the future we will meet again in the face-to-face meeting. But anyway, I give the floor back to you, Gergana, and I said, well, once again, welcome everybody.
Thank you, Maria. Okay, so let's turn to our first presentation. We have Massimo Candela, who is going to talk about his research on the impact of COVID-19 on latency. Massimo.
Thank you very much, Gergana. So good afternoon, or whatever time zone is where you are. I hope all of you are safe. So my name is Massimo Candela. I'm a senior software engineer at NTT, but this is a research with the University of Pisa, and in particular, I would like to thank my co-authors, Valerio Luconi and Professor Alessio Vecchio. So it is a research about the impact of the pandemic, in particular of the lockdowns, on the latencies of the internet. So initially this was presented the first time at RIPE 80 and released publicly on arXiv. The peer-reviewed version takes some time. I arrived a bit later, and is also available online since August, and it is essentially the first large-scale analysis of latencies, the impact on the latencies of the pandemic. So what we wanted to do here is to, in particular, compare the before and after. When I say before, or in particular week before, I mean 1 week where the coronavirus was not taken seriously. And when I say a week after, I mean we are all in lockdown. And I want to do that from a global point of view. I don't want to give like specific provider point of view or IXPs. And there are various reports from increases of traffic from various providers, but we believe that in particular the latency is gives a better hint of the impact on the network, because traffic only without information like capacity is difficult to give to have easy to interpret estimation. And we do it with a large data set that is composed of more than 12 billion latency samples. Of course, we use RIPE Atlas. Don't let me start about what RIPE Atlas is. You all know. So we use RIPE Atlas. And We want to consider the impact of the pandemic on the time of the day, the type of target, like, I don't know, it is content or not, IPv4 against IPv6. Also, numbers on packet loss, path changes, or HTTP latencies are reported. Of course, this presentation is really quick and will not have all this information, but they are available on the paper. So I'm going to start with the results for Italy for two main reasons. The first is that Italy was one of the countries that was earlier impacted by the pandemic and that the first to start with lockdowns. And the second reason is because I'm Italian. So, what I want to show you here is on the left, there is the anchor measurement, which are measurement autonomously carried out by the RIPE Atlas platform, mostly from probes, which are in home domestic connection towards target, which are anchors that are in the infrastructure of the net. But they are, as I said, automatically done. The one on the right instead is user-defined measurement, which are from the same probes, but toward whatever target the user wants to measure, like it could be Google, YouTube, but it could be also, I don't know, the pizza shop nearby, whatever. What we want to do here is we don't really care if your provider is faster, your latency is lower, or if your path is shorter or longer. What we want to do here is to see if for each source pair, we want to see if there is an increase of round trip time during the lockdown, an increase above the usual. The usual is what we consider the usual is the minimum of the latency that we are able to record on the 45 observed time span. In particular, for each source target pair, we detect the minimum round trip time. We subtract this minimum round trip time for all the other samples produced by the same pair. And we select only pairs that they are able to report at least data for 40 days out of the 45 that we monitor, so 90% of the time. Pretty stable. And they are millions of pairs that, and what you see, these three color line are this increase of round trip time. Also in both charts, you see a gray area on the left, which is the week before, so no lockdowns, and a gray area on the right, which is the week after, where we are in lockdown. You see there is an overall increase of round trip time. Where I say round trip time, I mean, again, this is above the minimum. But there is, I forgot to mention, the various dashed line are other partial event of lockdowns, which are also in the table here, bottom right. So what you see is that while the various lockdowns happen and while you get closer to the major lockdown or during the lockdown itself, there is an increase of the latency. There is also an increase of the variability, so the width of this line chart increases. But in particular, there is this effect of waves, which is particularly visible, especially in this data set on this side. And we were like thinking, okay, this must be these waves, is because all the remote working and all the people studying from home, so all this hard work it must done online, it must have impacted the network. But we were wrong, because we went to do a ratio between basically on the x-axis in this chart, you see the hour of the day, and we bucket the samples in 1 hour buckets, and we do a ratio of the week after divided the week before. This means that if you see values above 1, it means that during the lockdown it was worse, which is expected. But the thing that was slightly less expected is anyway, that is between 8 and 9 p.m. that we see that there is almost the double of the increase, which is probably entertainment. We try to confirm that by also selecting a subset of the measurements that they are involving, in this case, YouTube. But let's just focus only on the last two charts at the bottom. You see that this is scatter produced between 5 and 6 on the left and between 8 and 9 p.m. on the right. 5 and 6 during this time period and during and after the lockdown has an increase of latency, but really minimal. What you see between 8 and 9 instead is that in particular when the lockdown starts, the increase is considerable and it stays up for the rest of the monitoring time period. So now in the in the analysis, we report various other results for other countries. Here it was just a quick preview to stay in the under the 10 minutes. And I would like just to point out that there is among these countries, Sweden, which is one of the countries that didn't impose a lockdown, but it was suggested. And as many friends also referred to me, various people, they actually stayed home. And we can see that they have a similar pattern, also visually, we don't have it here, but a similar pattern to the other countries that actually did the mandatory lockdowns. So this was my quick presentation, and that's all. And if you have questions, I don't know if there is time for questions, that is the moment.
Yeah, we have a few minutes for questions.
Cool.
You can either post them in the chat, or you can unmute yourself and ask.
I'm glad that I stayed in your time limit.
Fantastic. Thanks, Massimo.
It will not happen again. I'm timing it.
I have a question, Massimo. Thanks for the presentation.
Thank
do you think, so what next? I mean, what could we do with this data? What we can predict? What is the main goal? How we can use this data in the future?
So actually there are various, okay, first of all, the data, I want to highlight how the importance of a platform like RIPE Atlas, because what we did here, we didn't measure anything. We used whatever the platform and the users were monitoring. So the first thing is another confirmation of how much constant measurements are helping in case of this natural, let's call it natural events, which could be also other natural events like hurricanes and things like this. Another thing that is something that we are investigating, or let's say we just plan to investigate, is the impact that such events have on other, not only the packet loss, but change in what we saw, but also things like active geolocation, for example, and other type of research. So are these natural events going to impact and how much, and things like this. This could be also an interesting future topic. So I don't know if I answer at least partially your question.
Yeah, exactly. So you mean like anomaly detection in the network when these big events happen, right?
Yeah, that is one which could be also done by, okay, it is difficult to automatically correlate to what is the reason, but it could definitely trigger alerts based on the RIPE Atlas monitoring, and could also trigger alerts to, for example, to know if a specific type of, give you an example. In my case, I do a lot of geolocation things. An alert like this could give us windows of when active geolocation, for example, is better to don't do it in that moment. In the case of the coronavirus, maybe the time window would be pretty big, but it would just give us some idea also on the quality of other type of research based on other type of numbers, calculations based on latency measurement, which are the moments that we can use or not use for doing this.
One moment.
Okay. Other questions?
Many thanks.
Although I think that, thank you for it.
Any other questions? If not, thank you very much, Massimo.
Thank you.
There is some, I've posted a link to the full study, and if there is, oh, I see a question from Vladislav. Since some RIPE Atlas probes are also at offices, do you notice latency decrease there?
So we did an analysis. Okay, so some probes are in the office, but the probes in the office are like really a small minority compared to the one at home. But anyway, what we saw that is interesting, that is related to the office, is the impact on IPv4 between IPv4 and IPv6. So if you compare dual stack probes, IPv4, IPv6, we see that IPv6 actually is not impacted all really almost not. Actually, if you see the plots that I don't have here, I'm sorry, you see that IPv6 during the lockdown or close to the lockdown goes slightly even better. The minimum round-trip time goes a bit better. And this is done by the fact, well, at least we suppose that is by the fact that there is no IPv6 at all. So essentially, the impact of the lockdown is not really so much visible on the domestic IPv6 because there is none. And while network improvements, which are also visible in some of our data and are confirmed by various operators, show that while the variability increases, the minimum values that usually are connected between 3 and 6 a.m., between 3 and 5 a.m., sometimes they are better. So sometimes during the lockdown, the latencies when the network is discharged went better. So this is clearly shows like between IPv6 and IPv4, it's one hint of also the differentiation between office use and domestic use.
Thanks. One more question from Mehmet Tahir. What about VPN? Did you use UDP? Did you see UDP increase?
No, we didn't monitor that. We don't have numbers for UDP or VPN. What we try to do is to get the biggest sample possible, and it is based on ICMP ping on. We have a HTTP measurements, but not UDP.
Right. Okay. Thank you so much, Massimo, again. If there is some time at the end of the session, I can open for questions for the paper again.
Sure.
Let me move on to the next talk. Anna Maria Mandalari. I've lined up all my Italians first. I'm realizing now. She's going to talk to us about IoT devices and their privacy implications.
Here we are. Okay, yeah. Perfect. Hello, everybody. I'm Anna Maria Mandalari, Research Associate, Imperial College London. Today, I'm going to present a summary of our recent work at Imperial on consumer IoT devices, privacy implications and mitigations. We know that any object nowadays can be connected to the internet, from smart speakers to cameras. Even your fridge can be connected to the internet. And we call these Internet of Things devices. And they're great. I mean, we can ask them to shop for us. Think about Alexa. They play music for us. But why are they so cheap? And what is the real value they give back to us? This is where my research journey started. I wanted to know what we are invisible trading in exchange for these devices. In this context, we need to talk about three things: privacy against gimmicks, how IoT devices expose privacy in a smart home, and most importantly, what might this mean for the future? So what if we are exchanging privacy for gimmicks and minor convenience? We are moving from buying a product to become a product. So the real question is, will consumers in the future choose to trade privacy for price? The reason of my research is that the main problem is that these devices are like a black hole. They can, by definition, access the internet and therefore may expose privacy information. There is a lack of understanding of what information the IoT devices expose, when they expose it, and to whom. And there is also a lack of understanding of regional differences in regulations. For example, GDPR here in Europe, it's not available overseas. So it's time to act, and quickly. Let's have a look in depth of how those devices violate our privacy. Let's see first, what is the destination of the IoT devices, what information is sent, and if they do something that we do not expect. So we wanted to do this purely, and we located the devices to the basement of Imperial College, and we bought about 123 different devices, from appliances to smart cameras, smart hubs, other home automation devices, from the most expensive to the cheapest one. And we located them in 2 different countries, US and UK. And we started testing them to see if we could answer this question that we had on the devices. We start capturing all the traffic that these devices are producing over the internet. We also built a mini testbed just for testing smart speakers, for understanding how, when, and why smart speakers are unexpectedly recording audio from their environment, and we call this misactivation. Our experiments used 125 hours of Netflix content from a variety of teams, and we repeat the task multiple times to understand which no-wake word can cause misactivation. We are also interested in whether there are trends based on certain no-wake words, type of conversation, location, and other factors. Let's see the first results. Most of the traffic from the UK lab is going to US or China. This is important because most of the traffic is behind Europe. The traffic from many categories of IoT devices is sent outside the testbed's privacy jurisdiction. We found other privacy violations. For example, some popular doorbell were recording at each motion and send the recording back to the cloud server in the country, even if you did opt out for that in the app. Popular smart television were contacting Facebook, Netflix, Google, and some advertisement trackers completely unexpectedly. And smart speakers were activating without saying the wake word. We detected smart speakers activated wrongly and therefore recording our conversation between 2 and 19 times per day. What we found is that most of the traffic is not going to the manufacturer, it's going somewhere else. That might be third party like trackers and advertisers. These devices are contacting destinations that are third party. After the contract you set up with your provider allows them to traffic your data to others, but we don't check, as terms and conditions are too vague. This enables a privacy risk, especially as you don't know who those third parties may be. The main problem is profiling. So based on the devices and the traffic from the devices, third parties can create a unique profile for you. Preferences, user interest, it's easy to see what you like and how you can be in some way influenced. So we will have a mass influencing. The void signal is a rich resource that discloses several possible states of speakers, such as emotional states, stress levels, physical condition, age, gender. Service providers can build a very accurate profile of a user's demographic category, personal preferences, and this may also compromise privacy. When we talk about the future of these devices, we know that Alexa, that is not today, won't be there. What happens when these devices become more like cognitive prosthetics, playing a future influence in your life and helping you make decisions about the most intimate of subjects, but accessing your data, the technology platform will learn your preference, anticipate your need and behavior, shop for you, monitor your health, and help your problem solve. I think that there is a more positive future at play. One where we achieve transparency and privacy by default for the user. So they know what is going on and what devices are trustworthy. I will explain some future applications on which we are working on in Imperial, and we will only see more sensor-embedded devices into our privacy, into our own. In my vision, we will see the control back to the hands of the consumer. We will use similar devices and they will have a benefit, but we will have an awareness on when our information is being used negatively. We will go against immutability and look for technology to be temporal and at the edge. So not at the cloud, but at the edge. So easily deleting anything that is sensitive. All the devices at use will be certified and trustworthy, where the manufacturer will have to declare the destinations the devices are contacting and the reason why they are contacting specific destinations, particularly third parties. So there is already a direction on that, and they're called manufacturer user description, MUD profiles. And it's a standard already, luckily. We will have third-party certificatory, and they will work as the certificates for the fridge nowadays. For example, giving work. So, for example, giving a mark including security, privacy, energy consumption of the device. One of the critical steps that will enable this is a solution at the edge. And not only at home, but also on the internet service provider. So we need solution directly at people's home. We need an automated framework for detecting and isolating non-critical, non-required communications from IoT devices. And we call this data box. In a way, data box will work like a firewall or an ad blocker for IoT devices that can be implemented on a home gateway. So we start investigating this, and we were able to block already 50% of destinations in a camera without breaking the main functionality of the camera that is streaming video. We will see this solution integrating into the routers, which means that every device that connects to them updates the terms and conditions accordingly. We will block the destinations and understanding if they are regulation compliant. So in conclusion, it's not all bad, because those devices can help us to reach a more comfortable life, or can help people affected, for example, by dementia, to live better and for longer in their homes, but we need regulations and supporting tools for protecting our privacy. Thank you. Here you have all my links to the works and my contact. Any question?
Thanks, Anna. Quick?
I'm muted. Go ahead, Randy.
Quick?
Yeah, what do you mean, quick?
Quick is very good at anonymous punching.
Yeah, exactly. The problem is not only the problem is not that you are using these. You don't have to think about these devices as a device in which you can install what you want, like a computer. It's something that comes with a firewall, and they cannot be touched. So you just buy a smart speaker. You put in your
But
home.
when they start using Quick, what the content of their traffic is will be much more difficult.
Yeah, I mean, it's always something that the user has to have in their home, right? It's not something that the
Your gateway has to detect the traffic from the IoT device, which, if it is using Quick to contact the first level broker, and it's going to be a broker, right? Just as ads are brokered. So you don't know where it's really going, and you can't inspect the content, is what I'm worried about.
Yeah, exactly. So it's okay. I mean, I know what you mean. It's something that you cannot really detect if this device is doing something wrong, because they can use security protocols. Okay, yeah. This is something that exactly. So there are many techniques on detecting the activity from the devices, even if the traffic is encrypted. So you can follow traffic patterns. You can we are doing this tool that is called IoTrimmer. We're working this tool on Databox that is called IoTrimmer, where we can test if blocking one destination is altering the functionality of the device. So you don't need to know what they are sending, but you know that you are blocking that set of destinations, the device still work. So let's say in the case of the camera, we blocked the 50% of the destination the camera was contacting, and we tested the functionality of the camera by streaming the video, taking screenshots, and for example, you can use machine learning for understanding if the video streamed or other techniques, and the camera was still function. So this is a technique that you can use. But yeah, I agree that sometimes you cannot really know what they are communicating with those destinations. But there are some techniques to understand this also if the traffic is encrypted.
We have two more questions. The first one is from James Blessing. You've covered the current state really well, but what about software updating?
Yeah. So this is like a problem. I mean, it's something that these techniques need to take in account that the firmware can be updated. So it means that they have to be refreshed periodically. And we are also working on this, trying to understand how many times you need to refresh your tool, your system, in order to face with updating.
Thank you. And another question from Robert Story. Have you looked at whether or not any of these devices might further invade privacy by snooping traffic on the local network?
No, we didn't, but it's something that we have planning to do it, because now we have data from 2 years from these 2 IoT testbeds. And we have also the local traffic, but we never, until now, we didn't have time to have a look at that, but we will.
All right. Thank you. Thank you so much, Anna. I think these are the questions for now. Again, if there is time for AOBs after all the presentations, and if there are more questions, I will come back to the presentations. I'm going to move to the third presenter now, John Christoph. He's going to share with us some of his RPKI research.
Thank you, Gagana. Hopefully I'm audible and you can see the slides okay. If not, please do.
Yeah.
Thanks for the invite, Gagana. So I am in Chicago and I'm affiliated primarily with 2 institutions. One is UIC, which is University of Illinois at Chicago, and the other is DePaul University. The former is the institution where I'm pursuing a PhD. So I'm a PhD candidate student there. And DePaul University is where I actually receive a salary. I work full-time. I'm a network architect at that institution. So I do more or less wear 2 hats. And if you can't tell, I don't know how well you can see the screen of me, but my hair is not as dark as it once was. So I'm an older PhD student. So I've been doing operations for quite some time and in the field of networks primarily. And so one of the areas that interests me revolves around internet infrastructure. So routing is one of those, DNS, denial of service hacks, those sorts of things. So one of the recent projects that I've been working on is something referred to as the RPKI, which I know at least one of you is very intimately familiar with this, but probably most of you have at least heard of it. But I'll give you a brief introduction to what it is and what we're doing here. And then if we have any questions, I'll be happy to try to field them. So the RPKI is really a specialized PKI, a public key infrastructure. The R stands for resource, but you could be forgiven if you equate the R in RPKI to routing, because it's really a special PKI for the NRPGP routing system. So let me show you a diagram that we use in the recent publication. It's a little bit busy, but it's broken up into more or less 3 parts. And if you look at the labels, vertically on the left-hand side, at the top we have the publication layer. So the RPKI repository consists of all the objects. So you start with things like the certificate authorities, those would essentially be your trusted roots, or in the RPKI, what we call the trust anchors. And the RPKI has 5 of those. Right is one of those. The other 4 are the other IRRs. And contained in the repository are a number of objects, but perhaps the one of most interested, the one that people tend to think of, are these things called ROAs, or route origin authorizations. And these are basically the mappings between IP prefixes and the origin ASNs that originate those prefixes in the routing system. Those are objects that get signed, they get published in the repository, and then that repository data can then be disseminated to anyone who wants to use it. Now, the repository is a distributed and delegated system. So while there are 5 trust anchors, it's not necessarily the case that there are only 5 places to go get the repository data. Each of those trust anchors can delegate a portion of that repository space, essentially downstream, to other ISPs or holders of the prefixes and the ASNs. And what makes that data available is called a publication point, or PP. It's just, you can think of it as a server. And all of that repository data is made available to this middle layer, this caching layer as we refer to it. And these are also referred to as relying parties. Now, relying party can be both a server and a client. When it's fetching data from the repository, it's a client, and it will do it using one of 2 or perhaps both synchronization protocols. rsync, which is a protocol that you're probably familiar with, and a newer, specially designed protocol for the RPKI called RRDP, or the RPKI Repository Delta Protocol, which you can literally just think of it as RPKI over HTTP. It's more or less the same thing. This relying party then can process that data, it can do the validation, it can check the expiration dates of certificates and all that sorts of stuff. It'll, once it's processed that, then it can make that process data available downstream to its client. So here's where it acts as a server to, what in effect, BGP routers. So typically the deployment models can vary, but you could imagine that relying parties would be run kind of like you might run a DNS resolver. In fact, they perform functions not unlike a DNS resolver, where they do caching and other things. And the publication points above are kind of like DNS authoritative servers, although the system is significantly different enough in at least one regard. The relying parties have to fetch all of the data from all of the publication points. Unlike DNS resolvers, which just fetches what clients ask for. So the relying parties have to have a copy of all the data, and they have to have a recent copy, what we refer to as timeliness of the data. If you don't, then the routers may be missing something. They might having stale information. They might not have a valid route that they should be checking against, or they might invalidate a route that it would otherwise be valid, and so forth. So that's kind of the overall architecture of the system from a very high level. Now, here I'm showing a couple of graphs that will be to appear in a paper that's coming in IMC, which I'll point to just shortly. On the left-hand side, we're looking at the frequency and the interval updates of relying parties to a publication point that we monitor using RRDP. So these are basically binned accesses. The positive side of the graph is from 2020, and the negative side is a day in 2019. We're just bin per minute, and we're looking at unique IP addresses, and we're saying, well, how frequently do each of these RPs synchronize, either using RDP or rsync, but RDP in this graph. And you can see they more or less line up, at least in this graph, with the popular default synchronization intervals of the software that's available for relying parties. There's a version of RIPE, which defaults to 2 minutes, RouteNator's 10 minutes, OctoRPKI is 20 minutes. You see less there, but it's just because it's less popular. And then other implementations tend to use cron tab entries, and or Fort, which uses a 60-minute default time interval, also somewhat less popular. Over on the right-hand side, we show a distribution of the popularity of the different implementations as we can determine them based on RDP. Since RDP runs over HTTP, they include the full HTTP user agent string tokens, and all the popular software includes an identifying string that signifies what implementation that they are, so we can easily identify who's who there. You can see who the most popular ones up until the end of April. I should point out, for those that haven't heard, RIPE has decreed that their implementation is going to cease development. It's going to run until, I think, July, the end of July or so. And it's fairly popular, so someone is going to get a fair share of that usage, I suspect, not long in the future. There's one other thing I'd like to tell you about, but this is where I'm going to encourage you to go look at the paper and our results. As we measured this, we found what we would consider a real major flaw in essentially all the implementations that do RDP. That will cause all of them in certain circumstances to lose access to a publication point. And so that's just a hint to go look at the paper, because we just don't have time to go into that. Here's the title slide of a talk we're going to do at IMC. You can see Brandy, who's with us today, is one of the co-authors. Some of you probably know some of these other people here. It's coming up in just a few days. And lastly, here's a link to some of the study data, the raw data, some plots, and some code, and then my contact information. So I hopefully did that in record time, but if we have time, I'm happy to take questions.
Perfect. Yes, thank you so much, John. Any questions from the audience? You can either type it in the chat or unmute yourself and just ask. James Blessing asks, any idea how popular rsync-based clients are?
They're not that popular. There's still quite a few of them. If you look at the sheer numbers, I didn't show this graph, but out of, let's say, if you take about a pool of 1,000 relying party clients, and I think today there's nearly 2,000 distinct RPs that we see. If you take about a pool of 1,000, about 200 of those will be rsync, sort of on average. So it's probably about a fifth.
All right, thank you. Any other questions? Baha, I see that you have raised your hand. You're unmuted.
Yeah, thank you. Yeah, thank you, John, for your interesting presentation. I read your paper. It's really interesting. However, I'm wondering how you will consider the last actually decision from RIPE NCC regarding the validator. So as you may know, the RIPE NCC actually decided to archive the validator. So I can see most of the network operator decided to change the validator if they use already a RIPE NCC validator to force or validator or something else. Do you consider something like that in your current study?
I think
because as I can see from your paper, I had to read your paper, honestly. So do you consider how will actually that affect the result and
I think
the RPKI structure or something like that? Yeah.
I'm sorry, I think I missed the first part of your question.
Okay, so let me repeat my question. So as you may know, the RIPE NCC decided to archive the validator. So I can see that there are a lot of network operators just change the current validator for their network to FORT validator or alternator, for example. So do you consider the effects of archive the RIPE NCC validator?
We don't. That announcement literally just came out. I only saw it within the last few days. So we certainly didn't have time for it for this paper, which was written, now weeks and months ago. I think we may see it though in our plots. We do show the distribution of software usage. So we may soon find out. As far as I know, today there hasn't really been any noticeable effect, although I haven't looked in the last couple of days. So I don't have an answer for you. I think it's just stay tuned.
Cool. So another question, please. I actually read in your paper, you established a test bed. So will that test bed will be publicly available for cooperation, something like that? Is it possible?
Well, all the data is certainly available. So you may download all the data that we make available. It's basically all the access log data. So if that's of interest to you, you're welcome to it. If you want to actually do something with the publication points, I think that's probably a discussion we could have offline. I can't make any promises there, but there is someone on this conference call that may want to chime in if he cares to.
Cool. Thank you so much.
Yep.
We'll send you an email, of course.
Okay, very good. Thank you.
Thank you.
Are there any
other questions I see?
I don't see anything in the chat. I hope I'm not missing anything. Well, thank you very much, John. If there's any other questions, we will handle them during the AOB time. So let me move on to our fourth presentation. Steve is going to talk about RIPE Atlas measurement data in BigQuery.
All right, thank you, Gorgana. Good afternoon, everybody. I hope you're having a wonderful afternoon. This is not a research talk. This is much more of a research support announcement, I guess. I don't need to describe to people here what RIPE Atlas is, because I figure you're probably already using RIPE Atlas. RIPE Atlas is continuously measuring the internet or parts of the internet, depending on where we actually are. The way that many people will use RIPE Atlas is they will set up a measurement campaign that they will have planned out in the past, and they will set up some measurements. They will get their little measurement IDs. They will fetch the results that they want to fetch, and then they will process those locally. Some people will download the data in bulk and then process that locally, which basically becomes an unwieldy problem, which is kind of beyond the standard realm of SED and awk and JQ and those kind of tools. Because fundamentally, we're running a lot of pings and a lot of trace routes and a lot of DNS queries and a lot of other types of measurements. And we're not at the billion mark yet, but we're on hundreds of millions of measurement results per day, which is, it's a lot of stuff to parse, and it fundamentally becomes a big data problem, and big data is a problem. So what we're announcing from today basically is that we've been putting data into BigQuery since maybe the last 18 months ago. If you were at or following RIPE 79, then you may have caught a presentation that I gave where I was talking about the prototypes that we were playing with at the time. Well, we've progressed from what was a prototype into something that we're now willing to refer to as a beta service that we're actually putting some engineering work into, and we're promising to at least support for the time being. So this is a direction that we're going in. This stuff is now available for people to go fetch. Robert's putting a number into the chat for how many measurement results we're grabbing right now. Basically, and I'm assuming these slides will be available somewhere or circulated after the session, we have a public project with data sets in it that anybody that has a Google account can go out there and start accessing. And within that project, we're basically exposing two data sets. I'm going to list these in reverse order. The first is a samples data set, which is 1% of 1 week's data in, this month, October. The purpose in this one is to give you a small data set that's representative of what's in the full data set that you can play with. It doesn't break the bank if you accidentally query the whole lot of it, which is perfect. It's great for sketching out example or prototype queries to give you a feel for how the service actually works. The other data set is our full fat measurements data set. And in there, we have measurement results for all of the main measurement types, DNS, traceroute, etc., running from January 1st, 2020 up to date. So the data that's going in there is being streamed in as we receive it. So it's about as up to date as you can get. You can follow within BigQuery, you can run queries against all of the incoming public data. To access this stuff, you do need a Google account. And the way that we see this working is that we are covering the storage side. So we're putting the data in there, we are managing that, we are paying for that part. We can't cover the costs for arbitrary queries from many people on the outside. So the cost of the queries is basically on you. And the good news is that unless you're going to be doing massive queries against many months of data, if you're going for full data set stuff, that can get expensive. But if you're doing ad hoc, quick, investigative type queries, a lot of that can be pretty cheap. So this is the direction that we're going with this. It's out there, you can access it. Some people will often ask why BigQuery, and the short version is that basically it can manage this sort of data set without flinching. Like the size of the RIPE Atlas data set is presumably nothing compared to what Google are actually running back there anyway. Plus the service operates as a data warehousing platform with an SQL interface on the top. It doesn't expose many operational concerns. So I never have to think about spinny disks or how much RAM an instance has or anything like that. Of course, you can still bump into physical limitations because of course there are machines back there, but in general, it hides a lot of that stuff so that you can get on with the real work of trying to answer whatever question you have about what's happening out there on the internet, be it today or on January 1st or on whatever other date in between. The queries on the system are pretty fast, albeit not lightning fast real time. They operate on the order of like seconds to minutes. So they're on a sort of a human scale. they fit within a nice iterative exploration sort of pacing. So if I have questions and I want to throw a query in, and then I realize that actually I was looking at the wrong thing or I got the query wrong, I can adjust and I can refocus and I can go in deeper. The other part is that this allows us to explore the data along basically any dimension. So we get to step away from measurement IDs and start to think about the data set in terms of, well, rather than a measurement ID, maybe I want all of the measurements coming from a subset of probes, or I care about all of the measurements regardless of type that are going to a particular destination, or I care about all of the trace routes that are passing through a particular subnet, for example. Like these are all prospects once we get into a general data warehousing platform like this. We are actively developing this. We are currently putting in measurement data. We're going to expand the window of data that we've got available in there. So right now we've got from January 1st, we're going to roll that back a little bit. So we've got more data from the past. We're going to add in other resources that are ours. So like probe metadata becomes especially useful. BGP data is extremely useful. These are things that we've prototyped with, but we're going to work on getting it right for the current beta also. So there is more on the way. And right now we've got a lot of data in there already that you can get at. As I say, this is a beta project, which means that if it breaks, we're promising that we'll fix it. But we're not necessarily promising that it will be around in its current form forever. There's an element of we are experimenting with this still. We're a small set of people, so we need some feedback from what people are actually using this for, what data works, what doesn't, and is there scope for building out additional data sets that make sense to you? So right now, we're putting in data that looks like the raw data that's coming out of Atlas. But maybe we can be smarter with this, and maybe we can augment data in ways that make sense in the general sense for a lot of people who are out there. We have links to more information. A couple of these posts went up in the last hour or so. So we've got a labs post that gives you similar announcement information to what you're getting right now. We have a static tools page that links you into all of this stuff. And we are putting like documentation, how-to, schemas, that kind of thing up onto GitHub, which is a much more active space that we're going to iterate on, and we're going to grow, tidy up, clear out stuff as we progress. So that's all under active development. And if there are questions, we have an email alias to send your questions to, atlas-bq@ripe.net. Send questions, send feedback, tell us if you're angry, tell us if you're happy. Let us know how you feel. And in general, we would like to kind of like understand what's going on and how people are using this. So like actually good feedback is good. And if you can tell us what works and what doesn't, that would be wonderful. And that's all I have. So that's me.
Thank you, Steve. I have 2 comments from the chat. Simon Lanen is saying, great initiative, very well explained, thanks a lot. Something like this could be useful for other data collections, for example, RIS, but maybe let's see how people use the Atlas one for a while. And then
I can speak to that point, which is that I do intend to put REST data in there. At least I've definitely prototyped with it, and I've got a good head for how to do things like prefix matching in the SQL interface that BigQuery exposes. So I actually would like to put that stuff up, because it's like coming from a more classical programming background like I do, it's a sort of a tough thing to fit into my head. And now that I've done the work, I feel like it should be shared. So some of that stuff will go up for sure.
That's cool. Thanks, Stephen.
Thank you. Vibraf is saying, very nice. Looking forward to stress testing it with students.
Perfect.
And then James Blessing is asking, does this mean you need to look at putting extra random probes into Atlas devices to enrich this project?
Random probes into Atlas devices. I'm not sure I follow the question. We tend to refer to the Atlas devices as probes. So unless you mean random measurements from the Atlas devices.
Yeah, sorry. Yeah, it was about just putting in random targets between different probes, so you've got stuff that people aren't actually currently asking for, but will make queries later have more data in them.
Yeah, so the data set is already pretty large because the user-defined measurements is not like the primary, it's not the bulk of the data. So all of the probes already do built-in measurements. They all run, for example, measurements to DNS root infrastructure, to Atlas controllers. They all participate in what we call topology measurements, where they will basically pick random targets generated from BGP tables. And they all participate in these measurements continuously. So there is a backing data set in there. We are always looking at like how we could improve that or how we could modify that to bring value. So like, yes, open question. Some of the data is kind of repetitive. Maybe you could argue it's redundant. How do we finesse that for Atlas? These are things that we're going to look at as we go forward for sure.
So thank you. I have some question if I can go. Yeah. So yeah, first of all, what is this RIPE Atlas thing now?
So RIPE Atlas.
So first of all, thank you very much. I think this is really useful. I'm going to use it a lot. Also, I think having the risk and the possibility, if in your plan can keep an eye on it, the possibility to easily correlate between the risk data and Atlas, that is something that has been always particularly difficult to do. And so that could help. So my question is, the first thing is, you said that there is a measurement, you call it a measurement data set, which is real time, and you refer as streaming. So what that, maybe you said it, and I missed it. So what exactly means? So what is the time span? Is it the last result for each source target pair? What is the?
That is every public measurement result that we're consuming.
But why you said, you said just real time in the sense that everything goes there in real time, not that it's just a snapshot that moves. That's what you mean, right?
Yeah. We're just feeding in results as they come in, and then we leave them there. We're storing them.
Okay, that's cool. That's cool. Okay, no, because I thought that there was some space related. Okay, perfect. And the second thing is that, are you already accepting like preview access? I don't know if you already said it. So
these data sets are public. You can go and look at them right now.
Oh, perfect. That's extremely cool.
And
Thank you very much.
If something breaks, that means that I screwed up in making them public. So you should definitely email that address and tell me, and then I can fix it. They should be public.
Perfect. That's perfect. That's all I want to know. Thank you very much.
No worries.
Thanks, Steve. I don't see any other questions. So I'm going to move to the last presentation for today. Robert Story is going to tell us about DNS identity and internet naming for experimentation and research project. Robert.
Yes, hello. I'm currently looking to figure out how to share the right window.
The window. It's the button is right next to chat.
I think.
The share screen. Yeah.
I think. Can you see my slides?
Yeah.
Okay, great. My name is Robert Story, and I work for the Information Sciences Institute, which is a part of the University of Southern California's School of Engineering. I'm a research programmer, and another part of what I do is I'm on the operation team for the B root server. So I have a lot to do with DNS. And like the previous presentation, this is not about a research paper, but a new research platform. So this is a brief overview of the presentation. This is normally given by my boss, Wes Hardiker. You guys are probably a lot more familiar with him than me. What we are looking at is being able to do research on DNS. So some of the questions and things that people might wonder about for DNS, it's not done. Is it? There are things changing, and there are questions like, what would happen if traffic continued to shift to newer protocols like QUIC, or that TCP was more used than a UDP, and we came up with a whole lot of questions. Wes's presentation has like 3 more slides on questions, but basically we want to be able to research how these changes might affect a system. And so it's difficult. A lot of research is done just based on packet captures and of traffic that has already passed, and you can't modify what's going on other than doing replay. So Diner is a research project funded by the NSF, and the idea is to make a collaborative infrastructure for researchers to perform research on DNS. And it builds on the B resolvers and authoritative server in our infrastructure. So this is what our infrastructure looks like right now, and pretty basic. Everybody does the same thing. You got requests, a load balancer that is sent to some nodes that respond to the queries. And so we want to be able to enable experiments on live traffic, right? So this is a basic overview of the goal, where we are going to split off traffic from our from one of our Anycast nodes in Los Angeles and send that traffic to a separate infrastructure for research. And this will allow people to experiment on live traffic, incoming traffic, without affecting our production system and the outgoing traffic. So in addition to live traffic, we want to be able to do research on repeatable results by replaying traffic, and not only traffic that could be generated from systems like DNSPerf, things like that, but we'll also provide a curated data set of events, interesting events that BRoot has seen. The traffic will be anonymized, of course, but it will let you simulate some large events. You know, just actually last week we had a 1.5 gigabit 5-minute window of traffic at one of our other Anycast nodes, and so that kind of data we'll be able to replay and let I missed a step. So in the pink box here on this, the experimental nodes, researchers will have access to this to be able to run their own software. So it's not just about analyzing what our system is doing, but experimentation can be to run different versions of the resolvers bind to not, if somebody's got a new one and they want to see how it compares to the production traffic. So either with the replay or live traffic. And so we have in front of the traffic, we have a query mutator, which would allow people to take the incoming traffic and say, well, what happens if we convert all the incoming traffic to TCP and send that through? And then on the other side of the experimental nodes, we have a capture system that will let you compare the results that are coming from the experiment that the researchers are running to the results that come out of the production system, and validate and make sure you're getting what you expect, in addition to be able to analyzing what's different. So ISI is a research institute, so we're already doing capture of the incoming and outgoing traffic that's processed through our Hadoop cluster. And that's the source of the curated data that we'll be able to provide. So for the infrastructure, we currently have the BRoot production streaming the data to a parallel test system, the same class of hardware. And we have set up a monitoring system to monitor the throughput and various metrics from the production system and the test system. There should be a check next to the stream replay and performance tool. There are several tools that we already have on the system for doing replay, and we're working on others. So we have some more long-term goals where we want to have our system automatically detect when odd things happen, like large events. I pointed out the inline system before the experimental node where traffic could be mutated. We're still working on that right now. We can do replay or live traffic, but we haven't got to the mutating yet. We're going to allow people to bring their own DNS. You can set up and serve different zones, test different resolvers and different software. And the system on the other side, the capture and comparison engine, is also still a work in progress. Right now, everything is done through shell access to these systems with SSH, but we have plans for getting a web console for controlling the data, switching between the live traffic and replay traffic, or selecting particular data sets that you want to look at and be able to manage experiments. So this is what our current implementation looks like. We are not streaming all the traffic that's coming in. We're just splitting the traffic off from one of our backend nodes that's going into the mutator system and then fed into the experimental node. So for the near term, we've just started this phase of the project with this hardware in place. And so we recently held a workshop back in July to discuss the needs and plans. And we're starting to look for getting people outside of our core team and some of the students from USC to be early adopters to test on the platform. We plan on continuing to have annual workshops and encourage collaboration and continue to work with researchers from other organizations. I stole these slides from Wes, who presented at DNS.org. So, you know, we're looking for getting researchers from wherever we can. This is an example of the graphing system that we have to compare the experimental versus the production systems. So in this instance, our Anycast node is running bind, and we put not on the test bed. There are some differences in the graph because right now, since we're using an optical splitter for the traffic, we haven't set up the query mutator at the front end to pass TCP traffic to simulate the TCP. So the production system has the mix of UDP and TCP, and the experimental system right now is only getting the UDP traffic. So that's basically what we're trying to do, is provide a platform for research on DNS. And so we're looking for collaborators. If anybody is interested in maybe getting on and beta testing, you can reach out to my boss, Wes Hardiker, or John Heidemann, who are the PIs for this project. And at the bottom of this slide, I also have the link for the project on the ISI website. And that's it. Made it just under the wire for 10 minutes.
Yes, thank you very much, Robert. Are there any questions from the audience? You could either post them in the chat or unmute yourself.
Hello. Actually, I would like to ask one question.
Sure.
There is a mutator in your system. I would like to understand if it is not just a reply mechanism, so it mutates based on some different domains, or it tries to mutate the actual behavior of the protocol. What's the case there?
So the intent is for it to be able to modify packets inline. So for example, to take the live traffic that's coming in, which is a mix of UDP, and say, well, what happens if we turn everything into TCP or DOE or QUIC? But really, that will also be available for researchers if you have something to modify the traffic inline that's going towards the experimental node. To do whatever kind of mutations you want, to tweak the EDNS buffer size, cookies. Basically a way to modify.
Actually, I think that could be a very nice addition if you would like to check bitwise modifications to see if a phishing DNS address is already there or not. So it could be beneficial. It could work as a fuzzer maybe for the DNS system.
Okay, yeah.
All right. Vladislav says in the chat that the IXP.mk definitely needs a root server locally and is willing to contribute, maybe a B root, and he's not sure what traffic levels are expected.
Okay. So you can send an email to us at b-poc, stands for point of contact, at isi.edu. And that will go to all the team, and you'll get a response from Wes. We often get requests for hosting B-root instances. I think as we've been expanding B in the past 3 years has gone from a single node to 6 Anycast sites now. And for the most part, it's probably around or under 50,000 queries per second at each Anycast site when they're all up and sharing the traffic load.
All right, thank you, Robert.
Mm-hmm.
I don't see any other questions in the chat. I don't see any hands either. So yeah, thank you again. This was the last of our presentations for today. I want to ask you if you have any quick announcement to make, any AOB at the end of the session, because we're nearing the end.
Because it has to be said.
Yes.
There's more. There's of course there's more root server operators. So if somebody wants to offer to host a root server, they should probably contact all of them.
Thanks, Daniel. Steve, I saw.
Can I throw up one slide?
Yeah, sure.
I'm not wearing my RIPE NCC hat. So quick advert, we're over time. Coming up is the deadline for the Applied Networking Research Prize. I'm on the review committee for that this year, and we're trying to diversify the set of candidates that we get nominations from. So you nominate a paper that you've recently read. You don't need to do new research to get into this. You nominate a paper that you've recently read, and the winner of this gets money to go and attend an IETF meeting, assuming that those eventually happen again in the future. And you get cash and recognition and fame and all of these good things. Deadline's coming up soon, and we've got a RIPE meeting this week in IMC, and so we're going to have a lot of papers out there. So if you see something good, approach them, try and encourage them to nominate themselves for NRP. That's me.
All right.
If I nominate a really good paper, can I get a ticket not to go to an IETF meeting?
Do you have that choice?
Thanks, Steve. I don't see any other hands or comments, so I'm assuming there are no other AOBs. Thank you very much, everyone, for attending. I hope you enjoyed this session. I will try to email you a recording of it as soon as I have it. Judging by last RIPE meetings experience, it's going to take our web services team about a week to upload the video, because they're busy with the RIPE meeting going on. So if you don't hear from me this week, don't worry, the recording is still coming, and I will email it to you as soon as it's online. Thank you very much again for attending, and have a lovely day.
Thanks, Gergana.
Thank you, Gergana. Bye-bye, everybody.
Bye-bye. Thank you very much. Bye.